Okay, so when we play with the Play-Doh, we see that when we measure the voltage, keeping one probe and one end of the Play-Doh, and we move the other probe, that the voltage was increasing, increasing, increasing. And then when we measured the voltage or the potential difference across a little segment and the potential difference across a adjacent segment, then the addition of those two was equal to the voltage across the whole segment. So that verifies that the voltage, the total voltage across those resistors that are in series with each other is equal to the voltage across the whole thing. Now, what if we look at our parallel ones? That's what I was going to do. So here is our battery. And we took one wire and connected it to one little cylindrical looking slug grub, and then we took another wire and connected it over here to this dude that was cut, right? We have one piece and we cut it long ways, and then we connected these wires, and then we went back to the battery. Now hopefully when you measured the potential difference across here, it was equal to the potential difference across here, or pretty close. And so that idea is that the potential difference they're equal for parallel resistors. Now we played with the Play-Doh and we looked at what does changing the geometry of the Play-Doh do to the system. So we changed the geometry. First, we did test what's happening with length. When we make it longer and longer and longer, we got that this resistance across here would be like R, but this resistance across here when it was longer would be like R, and then the resistance across the whole thing would be like big R. So the resistance was proportional to the length. Now, you guys took the Play-Doh and you started out with a short little grub and you measured the voltage across it. And then you added to that grub but kept his length constant because that's what good scientists do. And then we even made him even bigger, keeping the length constant. And what did we find out about the voltage? The voltage decreased, therefore the resistance was decreasing. So R is indirectly related to the area, the cross-sectional area. So let me mark what that looks like. This is the cross-sectional area. The area of the base of a cylinder, if you want to go there. Okay, so let's put that together. When we put that together, we'll see that the resistance is equal to the length divided by the area, but then it depends on the material. Some materials are more conductive. Some materials are less conductive. So that constant for the material is this rho, and it's called the resistivity. The resistivity. So R stands for resistance. Measured in ohms. L is the length of the conductor or the length of the piece of wire. What would it be measured in?
Meters.
And then A is the cross-sectional area. would be in meters squared. So what would resistivity have to be measured in order to satisfy this equation? Definitely meter, because I have a meter squared on the bottom, and I have a meter on the top. So I'd have to have a meter. So that would give me ohms is equal to meter squared over meter squared. Is that true?
No.
You need an ohm in there.
So it's a meter ohm meter?
An ohm meter.
Ohm meter.
So our resistance is going to depend on the geometry of the actual material. So we could look at a rectangular prism, like a block of iron or something like that, where this would be the length, this would be the cross-sectional area, and then we would look up the constant. So rho is constant for particular materials. Oh my goodness. Omega. What if don't I like to give you graphs where like the slope is the constant? Oh my goodness. Okay. So what if we varied the length? So we changed the length and then we measured the resistance with an ohm meter, which is one of the functions of your multimeter that you have on your desk. It has a little symbol called an ohm in there. So we get the lengths, we get the resistances. How could you find the resistivity from that information? What else would you need to know about this conductor? The area. So we would have to know the area. The cross-sectional area. So what would you graph?
We graph in the y it would have to be R, and then in the x it would be L over A.
Think about the circuit or the equation in terms of y equals mx. There's no plus b. So m, what would m be? What would the slope be? Yeah, we want it to be rho. Now it can be rho over a because that's also constant, or it can just be rho. If you wanted the slope to be rho, what would you have to put on the y-axis? The resistance. And what would you have to put on your x-axis? L over A. And that's one option. And then when you got your slope, so anytime you have a fundamental physics equation, you should be able to look at it in terms of y equals mx plus b, at least to help you figure out what the relationship is. All right, let's try a few examples.